In this lesson, we'll continue our discussion on big idea number 1. What are redox reactions and how do you describe them? And we'll complete learning target number 1. By the end of this lesson, you should be able to identify when a redox reaction occurs and describe the reaction using proper terminology. And we'll focus on representing redox reactions using oxidation numbers. Redox reactions occur with molecular compounds as well as ionic. However, since electrons are shared in covalent bonds, you can't use ionic charges to describe electrons being transferred and identifying redox reactions using this method. Oxidation numbers were developed so that you can easily see redox reactions involving molecular compounds without charges. Oxidation numbers are actual or hypothetical charges assigned to atoms using a set of accepted rules and patterns. Oxidation numbers were first assigned by using Lewis diagrams. They are always written with the sign first, then the number. This is the opposite of ionic charges. For example, oxygen usually has an oxidation number of -2, but the oxide ion has a charge of 2-. Make sure you follow this convention. To assign oxidation numbers using a Lewis diagram, follow the steps below. First, you need to draw the Lewis structure of the compound. Then, determine which atom in each bond is more electronegative. Pretend that this stronger atom owns the shared electrons. Then, assign an oxidation number equal to the charge that element would have if it was an ion. Here's some examples. Because oxygen is more electronegative than hydrogen, we are going to pretend that it actually steals the electrons it is sharing with the hydrogens completely. That means that the oxygen will steal 1 electron from this hydrogen, 1 electron from this hydrogen, meaning that it would have a charge of 2-. So we give it an oxidation number of -2. Because the hydrogens have effectively lost an electron, we give it an oxidation number of +1. Here's the Lewis diagram for F2. Because they have exactly the same electronegativity, they will not gain or lose an electron. Therefore, they will have an oxidation number of 0. Finally, CO2. O is stronger in its electronegativity than carbon is. Because each O will pull on 2 electrons, we will give them an oxidation number of -2. And because the carbon is losing 4 electrons, it will have an oxidation number of +4. Now, can you imagine drawing Lewis structures and assigning oxidation numbers using this method for every chemical in every redox reaction you want to examine? It would take a lot of work. So chemists have noticed patterns which allow us to determine oxidation numbers without drawing Lewis diagrams. Number 1, any pure element has an oxidation number of 0. because they're sharing electrons equally. So for example, Br in a Br2 equals 0. The oxidation number of any ion equals the charge on the ion. So an Al3+ has an oxidation number equaling +3. Hydrogen in a compound always has an oxidation number of +1, with one exception, in metal hydrides where it equals a -1. Oxygen usually has an oxidation number of -2, except in peroxides like H2O2 and the compound OF2. In molecular compounds that don't contain hydrogen or oxygen, the more electronegative element is assigned an oxidation number that equals the negative charge it usually has in an ionic compound. For example, in the compound PCl3, because chlorine is more electronegative than phosphorus, it is assigned an oxidation number of -1, which is chlorine's typical charge. The sum of the oxidation numbers in a compound must equal 0. Therefore, if in the compound CF4, the fluorine, because it's more electronegative, would equal its charge, so therefore -1. The oxidation number on the carbon must balance out the 4 fluorines. Because each fluorine is a -1, and I have 4 of them, that's a -4 that needs to balance. Therefore, the carbon must have an oxidation number of +4. And finally, the sum of the oxidation numbers in a polyatomic ion must equal the charge on the ion. For example, in NO2 1-, the oxygen equals -2. Because I have 2 of them, then I have a -4. But I need to leave a charge of 1-. So therefore, nitrogen must equal a +3. Pause the video here and assign oxidation numbers for each element in the compounds in example 2. Here are the answers for example 2. SiBr4. Because this compound does not contain H or O, we assign the more electronegative element, bromine, to have an oxidation number equal to its charge. So each bromine will have an oxidation number of -1. Now the sum of the oxidation numbers have to add up to 0. Because I have 4 bromines, then the silicon must cancel out a -4. So it will have an oxidation number of +4. Because iodine is an element, it will have an oxidation number of 0. HNO3. Hydrogen will be a +1, and each oxygen will be a -2. The nitrogen has to balance the charge to 0. Because I have 3 oxygens, that gives me a -6. But because of the 1 hydrogen, that gives me a -5. Therefore, the nitrogen must balance the remainder and be a +5. Cr2O7 2-. Each oxygen is a -2. I have 7 of them, so that's a -14. But because the charge is a 2-, I need to leave 2, which means I have a -12. That is spread over 2 chromium atoms. So 12 divided by 2, each chromium will be a +6. Oxidation and reduction reactions can be defined in different ways. We've already seen in organic chemistry that if the number of CO bonds increases in our organic compound, we call it an oxidation. But if the CO bonds get reduced, it's known as reduction. In the previous lesson, oxidation is defined as being the loss of electrons. But how does oxidation number play into this? If in the course of a reaction the oxidation number of an element increases, that is also defined as that element being oxidized. Reduction in the previous lesson was defined as the gain of electrons. If the oxidation number of an element also decreases in a reaction, that can also be used to identify a reduction. Here's an example. In the previous lesson, we wrote half reactions for the following net ionic equation in example 3. In order for the zinc to turn into a zinc 2 plus ion, it needed to lose 2 electrons. And in order for the copper 2 plus to change into a copper solid, it needed to gain electrons. Thus we had an oxidation and a reduction. Let's write oxidation numbers for each of these compounds in the half reactions. Because zinc is an element, it would have an oxidation number of 0. And because the zinc 2 plus is an ion, it has an oxidation number equal to its charge. Therefore, this is an oxidation because the oxidation number of the zinc increased by 2. Let's check out the oxidation numbers in the reduction. Because Cu2 plus is an ion, it has an oxidation number equal to its charge, plus 2. And because Cu solid is an element, it has an oxidation number of 0. Therefore, this is a reduction because the oxidation number decreased. Pause the video and try out example number 4. Using oxidation numbers, determine if a redox reaction occurred, and if so, identify the oxidizing and the reducing agents. Here are the answers for example 4. Notice that in question A, none of the compounds have charges. This is why using the oxidation number method is a lot easier than keeping track of electrons being transferred. Start by writing oxidation numbers for each element in the following compounds. For CH4, hydrogen will have a plus 1. In order to balance to 0, it means that carbon must have a minus 4. F2 will be a 0 because it's an element. In CH3F, hydrogen will have a plus 1, and because fluorine is the more electronegative than carbon, it will have an oxidation number equal to its charge, minus 1. That means in order for the compound to balance to 0, this carbon must have a minus 2. And for HF, plus 1 and minus 1. In redox reactions, you'll see elements that change oxidation numbers. And this is indeed a redox reaction. We have fluorine going from a 0 to a minus 1, and we have a carbon going from a minus 4 to a minus 2. Because the oxidation number of the carbon went up, it got oxidized. Therefore, it's known as the reducing agent. And because the oxidation number of the fluorine went down, it got reduced. Therefore, it caused the carbon to be oxidized, so it is known as the oxidizing agent. Let's look at example B. Because CaSO3 is an ionic compound, there's a couple different strategies that you could use. I always tend to look at the oxygens first. They have to be a -2. Because this is an ionic compound, I have a Ca that's got a 2+, so the calcium must have a +2 oxidation number. The sulfur must balance everything out to 0. Because I have 3 oxygens at a -2, that gives me a -6. The calcium takes care of 2 of those, so the sulfur needs to balance a -4, so it will be +4. In HCl, the hydrogen will be +1, leaving the chlorine -1. In calcium chloride, the calcium will be a +2 and the chlorine will be a -1. +1 and -2 for the water, and -2 for the oxygen. Because I have 2 of them, that gives me a -4 for the sulfur to balance, so it will have an oxidation number of +4. Now notice that none of the elements change oxidation numbers. Therefore, there is no redox reaction here. And finally, example C, something from our organic chemistry unit. Remember that square brackets O is code for an oxidizing agent. If we have an alcohol with 1 CO bond and we oxidize it, we will need an organic with 2 CO bonds. That will give us an aldehyde. The oxidizing agent must remove 2 hydrogens from the organic in order to achieve this. Instead of doing it the organic way, we can use oxidation numbers. Each hydrogen will be a +1. And the oxygen will be a -2. In order to add to this 0, the carbon will then need to be a -2 as well. Because we don't know what the oxidizing agent is, let's assign it an oxidation number of 0. In our aldehyde, each hydrogen is a +1 and the oxygen is the -2. So therefore, our carbon, in order to balance, needs to be 0. The hydrogens attached to our oxidizing agent will be +1. So therefore, the oxidizing agent must have an oxidation number now of -2, so it balances to 0. Because our carbon goes from a -2 to a 0, its oxidation number went up. Therefore, it got oxidized, and therefore the carbon is the reducing agent. Because the oxidation number of the oxidizing agent went down from 0 to -2, it got reduced, which is why it's called the oxidizing agent.